Today we're going to be talking about logarithmic functions. And I've mentioned logarithmic functions only vaguely. And I've told you guys that Module 4 is all about exponential functions and their inverses, logarithms. Okay, so we're going to introduce the idea of logarithms today, and then we're going to graph some logarithms. But first, I want to do a little bit of a review, talk about what logarithms are and how we construct them. The notation for logarithms can be a little bit alarming or maybe a little bit weird, so we're going to have to get to that notation. But fundamentally, just like that example that we talked about in a previous lecture where I said, imagine that you're an American and you're traveling to Mexico. We want to convert our currency over to Mexican pesos, and then we want to convert that stuff back to dollars when we come back from our trip. In the world of exponentials and logarithms, we're going to have to do a lot of this stuff where we convert exponential equations over to logarithmic equations and vice versa. Because sometimes when we're solving equations, they're easier to solve in exponential form. But when that's not the case, usually we can make a conversion to logarithmic form, and then that's going to make the equation a lot easier to solve. So we're going to solve those types of equations starting on Monday. But for now, we have to introduce logarithmic functions and look at their graphs, kind of do some compare and contrast with those exponential functions that we talked about yesterday. Okay. So what is a logarithmic function? To understand these functions, we need to review two things. What's an exponential function, right? And what is an inverse function? Okay. So just remember, based on our lecture from yesterday, an exponential function takes the form f of x is equal to b to the x power. Hold on. Can you guys still see the PowerPoint?
Yes.
Okay, I accidentally hit a button and I paused the screen sharing. Let me stop this real quick. Some technical difficulties here. All right. I was like, I don't know what button I pressed, but I pressed the button. Okay. So let's see. Still recording. Let's go. All right. So the exponential functions take this form over here, and we call them exponential functions because usually for any function, we take an input that we call an x value, and we plug it into the function. Well, for exponential functions, that input is going to appear in the exponent, and that's why we call them exponential functions, okay? But this number at the bottom of that exponential equation, we call that the base of the function. The exponent x is going to be what we're changing. And so yesterday we built this function f of x is equal to 2 to the x power. We graphed it on paper. And so I don't want to do that necessarily, but in this PowerPoint, in the next slide, I just briefly show you this is the graph of an exponential function of base 2. Okay. So that's f of x is equal to 2 to the x power. Remember, we could find all the y values we need by simply setting up a table of our x values and then figuring out what the y values are. So for instance, if I chose 0 for my x value, then I can evaluate that at 2 to the 0 power and get a y value of 1. And that's where we're getting this point 0, comma 1, which happens to be the y-intercept. If I plugged in 1, then that would be 2 to the 1 power, and we would get a positive 2. So 1 comma 2 would be your next point, and we could continue doing that, and so on and so forth, okay? So we built these functions, and we saw some properties of all of these exponential functions, at least their parent function. So if we don't transform them by shifting them to the left or to the right, if we don't shift them up or down or have any kind of weird reflections, then they all will have this y-intercept at 0, comma 1. They're all going to have a horizontal asymptote that kind of overlap the x-axis. So down here, we have this dashed red line. Okay, that's our horizontal asymptote. If you just kind of eyeball the graph and ask yourself, what's the domain? Remember, the domain is measuring how wide is the graph. So my graph goes all the way out to negative infinity on the left. And then if I sort of watch this graph go out to the right, it gradually goes out to the right and doesn't stop pushing out to the right. So you can think of it like a wave, like that wall of the tsunami. as it's pushing out to the right, we're going to say this graph is going to go all the way to positive infinity. Okay, so that's where we're getting this domain from. The range, on the other hand, is how tall is this graph, right? What's the lowest y value that belongs to this graph? And then what's the highest y value for this graph? And so if you think about the floor of the graph being that horizontal asymptote, that horizontal asymptote is at a y value of 0. And the graph starts at that horizontal asymptote and then continues to climb up all the way as it approaches positive infinity. So we're going to say that this graph goes from 0 to positive infinity. And so that's our range. Okay, does anybody have any questions about that? Like really quick recap. Again, I don't want to linger too much on that because that's the topic of yesterday's lecture, but any questions, comments about this exponential function?
No.
Okay. So then, the first lecture from Module 4 said or introduced this idea of an inverse. And an inverse function, if I have this original, let's say f of x is the OG function. If you have an xy pair for this original function, then we can convert this and figure out what the inverse function is. And that's usually written as f with a little -1 exponent. We say f inverse. It's not technically an exponent, even though it looks like one. So f inverse, if we have x comma y for the original function, then the ordered pair that we can get for the inverse function is going to swap that y and that x. So we have y comma x. So for instance, if I had 0 comma 1 for this exponential function, then its inverse function is going to have the point 1 comma 0, where I just swap the position of the coordinates. If the original function has this 1 comma 2, then my inverse function is going to have a point at 2 comma 1. Do you guys remember that stuff?
Yeah.
Yes, sir.
Okay.
At least.
And like that stuff should have been pretty straightforward. Hopefully, when you guys got into that homework for inverse functions, that was kind of maybe with a little bit of practice, became a little bit easy to see that, oh, that's all we're doing. We're swapping the x and the y values. Okay. Well, what this means is that if we have this graph and these ordered pairs for this exponential function, all we need to do is write down a list or a table where we swap the x and the y values, and then that will give us a set of ordered pairs where we can now graph the inverse function, which is a logarithmic function, okay? So based on property 1 of inverses, or yeah, of inverse functions, all we need to do is swap the xy pairs to y comma x, and then that new point belongs to the inverse, okay? So if we have our domain for our original function, let's say we have the x values -1, 0, 1, and 2, then we should be getting this range 1/2, 1, 2, and 4. Okay, and remember, the original function we're working with is f of x is 2 to the x power. Okay, so these numbers, these x values, are just numbers that we chose arbitrarily. And so if I plug, for instance, 2 to the -1 power, yesterday we introduced this negative exponent rule, which said if we have a negative exponent, we'll flip this to a fraction, 1/2, and then we'll apply the 1 power. And so that's how we're getting this y value here. Okay. With this one, if we take 2 to the 0 power, that's going to equal 1, and that's how we're getting this value here. Okay. But those inverse functions are really nice because they're going to reverse this process. Okay, so we might not have the equation for the inverse function that we're sort of kind of alluding to here, but fundamentally, we don't need that equation because whatever the y values are over here, we're trying to say if we have this y value here and we know it came from this x value, then if I plug, for instance, f inverse of 1/2 into the inverse function, then it should take this number and then return to me the original x value. Okay. And that's kind of the motivation for why we wanted these to be one-to-one functions, so that we can make a forwards conversion and then a backwards conversion without losing any information. So for instance, I should be able to take this 2 and plug it into the inverse function like so. And again, I don't care what the equation is right now, but in theory, if I plug 2 from the range into the inverse function, that should get me back to this x value that it came from originally. Does that kind of make sense? Or are
Yes.
there any questions there? Okay. So we're just trying to get this backward conversion property so that we can do some really interesting things with some equations here in a second. Okay. So we're not going to concern ourselves with what this equation is for the inverse. All we need to know is that it exists because our exponential function is a one-to-one function, and all one-to-one functions have inverses. So the inverse for this function, 2 to the x power, must exist. Okay? So we can construct this inverse, at least its graph, without even having the equation for it, right? By first setting up our table for our exponential function. Okay, so this table just represents our exponential function. I'm going to put exp just to abbreviate exponential function. And we can find all the y values over here by simply taking 2 to the -1 power, and that's giving us the 1/2. 2 to the 0 power is giving us the 1, and so on and so forth. Okay. But we did this when we introduced that idea of converting currency, right? From dollars to pesos and then pesos to dollars. All we have to do is take this table, the x and y values, and swap their positions. So by doing so, we'll get the inverse function table that represents the inverse of the base 2 exponential function. Okay. So all we did here, again, is take these x values, the domain of our function, just going to put domain, and then we said, let's take those numbers, and that's now going to become the range of the inverse. And I'm just going to put f inverse here. Okay. Then all we did was take these values that were originally the range of our exponential function, and then those got swapped, and so they became the domain of the inverse. Are you guys okay with that?
Yes.
Yes, sir.
Okay. So what I'm going to do is I'm going to write both of these tables down, and just bear with me for a second. So we have an x and y table here. This is our exponential function. F of x is equal to 2 to the x, and we have -1, 1/2. We have 0, 1, 1 and 2, 2 and 4. And then over here for our inverse function, which we don't know its equation, but now we have its x and y values, and we have that at 1/2 comma -1, 1 comma 0, 2 comma 1, and 4 comma 2. And then as you guys know, I always like to take this to pencil and paper because I think that makes a little bit more sense to see a human work these problems out. The original generative AI. Okay. So we have our function table for our exponential function, and then we have this inverse function. So guess what? We're going to graph these by hand just so we can see what these graphs look like when they're graphed together. Okay, so I'm going to draw my x-axis here and my y-axis here. And let's graph this one, and I'm going to try to color code them. You probably won't be able to see this very well. This is a blue pen now. So my original function is going to be graphed in blue. Okay, so we have, let's count by ones. Let's say this is 1, 2, 3. This is -1, -2, -3. And then our y values need to go up to 4. So let's say this is 1, 2, 3, 4. And then I'll go down 4 as well. But it's going to get really busy if I label those, so I'm not going to label those. Just know that we counted by ones. Okay. We're going to plot these now. So I'm going to take -1 and 1/2. That's -1, and then up about a halfway. There's my first point. 0, comma 1 is start at 0, then go up 1. There's our y-intercept. Over 1, up 2. Over 2, up 4. And then just remembering we have a horizontal asymptote on the x-axis, so I'm just going to draw a curved line that passes through these, like so. And so this is going to represent our exponential function, right? F of x is equal to 2x. Okay, do you guys need a little bit of time to sort of process that and draw that yourselves, or am I okay to keep going?
I think you're good to go.
Okay, thank you. So I'm going to color code the inverse function in red. There's nothing wrong with the inverse function, but it's kind of acting as the villain here, I guess, in this story. We're just going to take these ordered pairs and then graph them on the same graphing space. So we're going to go to 1/2 on the x-axis, then go down 1. So that's going to be like right here. We're going to go over 1 and then up 0. So over 1, and then we're not going to move at all. So that's going to be an x-intercept now. Then we have 2, comma 1. So that's over 2, up 1. And then this one's over 4, up 2. So I didn't count enough out. So that's going to be 4, and then up 2, like here-ish. And then if you remember, I said that whenever you plot the original function with its inverse, they should form this sort of reflection across this diagonal line that we sometimes call the identity function. But it should make a perfect reflection. So if I were to just like fold my paper over that diagonal line, then those points should fall on top of each other. And so we should get a graph that looks something like this when we curve it out and extend it. And this represents our inverse function. And this inverse function, here's the big reveal. We said we don't have the equation for it, but we don't need it. What we're going to do is just call this log base 2 of x. Okay. Log base 2. Okay. So the word logarithm literally just means the inverse of some exponential function. And so for every exponential function, we said this is an exponential of base 2. When we build the logarithmic function from this exponential, we have to label it with this little subscript 2 so that we know this is the inverse for the exponential base 2. And that's why we call it log base 2. Okay. Now there's also some really interesting properties now that we have reflected that original function over that diagonal line. And that is now this point here at 1, comma 0 is an x-intercept, where originally for the exponential function, that was a y-intercept. Okay. So when we flip this point over that line, it got placed onto the x-axis instead of the y-axis. Okay. Also, for this exponential function, we said originally it had a horizontal asymptote. But now, once we made that reflection, this graph here looks like it has a vertical asymptote that would be sort of overlapping the y-axis. So our logarithmic functions are going to have a vertical asymptote. at x equals 0, which is overlapping the y-axis. And then we could say, well, not paying attention to this function, right? Let's just focus on our inverse function here. Can you guys tell me what the domain of this inverse function is? Remember, we're trying to measure how far to the left does this graph go?
The domain should be negative infinity to positive infinity.
No, no, no. So that was the domain of the inverse, I'm sorry, of the exponential function.
Okay.
But if you look at this inverse function and we see, like, let's trace it as we go to the left.
Okay.
Yeah, we just do it in reverse, right?
Yeah, it's in reverse.
Yeah, it's kind of in reverse. Or as I said before, the domain of this function becomes the range of this function,
Mhm.
and the range of this function becomes the
Becomes the
domain of
domain.
this function.
This
So,
function.
but like just visually looking at the graph, and we, keep using that rule of thumb that the domain is like the leftmost part of the graph. This graph goes left and gets blocked by the y-axis, right? And so that x value that we're stopping at is x equals 0. So the domain on the left side starts at 0, and then the graph continues to move to the right. And as we walk to the right, we're going towards positive infinity. Does that make sense?
Yes.
Right. And then the range of the graph is what is the bottom of this graph? So if we trace this graph down, the graph is going down towards negative infinity, it looks like. So negative infinity is going to be the start of the range. And then this graph goes up. And even though it's kind of just gradually going up and it seems to slow down here, it is still going up. So we're going to say that as this goes out and up, it's kind of getting taller and taller. So we're going to say that's getting towards positive infinity.
Positive infinity.
Okay. And remember, this is kind of swapped over from the domain and range of this exponential function. So the domain of this function goes from negative infinity to positive infinity. And the range of the exponential, well, the bottom of this graph starts at a y value of 0, and then the graph goes up towards positive infinity. So at the risk of sort of making this busier than it needs to be, remember that the domain of your original function becomes the range of the inverse because those are the same, right? Negative infinity to positive infinity, negative infinity to positive infinity. And then the
Hmm.
range of the original function becomes the domain of the inverse. And you can see that those are the same. 0 to infinity, 0 to infinity. So their domain and ranges get swapped. Okay, so I'm going to give you guys a moment to sort of process that emotionally and spiritually, and then we'll start, looking more into logarithmic functions. But the first one's always going to be like, this is the full story, right? And then it's like, okay, now that we've seen it all play out, let's see what we need to do with this, because it's kind of a lot of information. But now we're going to do some specific work with these logarithmic functions now that we have sort of the background context. Any questions or comments before we move on? Are you guys ready?
Yes, sir.
I'm ready.
All right. Okay. So we graphed the inverse function already, which is a big reveal. Here we have on the next slide. We have the exponential function in blue, and we have the inverse function log base 2 of x in orange. Okay. So remember, we could have done this kind of demonstration with any exponential function. Like what I mean by that is I could take, instead of 2 to the x power, we could have done 5 to the x power, right? Made an xy table, taken those ordered pairs, whatever they happen to be, switch them, and we would have found something that we're going to call log base 5 of x. And so what you have to understand here is that even though we're not going to do that over and over again, the simple fact is that there's a lot of different exponential functions that all have different bases. Last class, or in the last PowerPoint, we saw 2 to the x power, 3 to the x power, and 4 to the x power. Those are 3 different exponential functions. So each of them, having their own distinct base, will have some inverse, which is its own distinct logarithm. Okay? So to understand this, I think it's really good to practice understanding this notation. Log base b is written this way, where we put log with this little b down here to indicate the base. And one way to think about that is it's telling you what exponential function it comes from, right? It tells you what exponential function it's the inverse of, okay? And as we start solving some equations later, we're going to see that like inverse functions cancel each other out. And so that's going to be a really useful property later on, okay? So for now, what I'm going to sort of do a little mini quiz on is if I have log base 3 of x, can you tell me which exponential function that this logarithm corresponds to? So
The
if I have
third
log
power?
base 3, no, go ahead. Can you repeat that?
Is it the third power?
It's not the third power, because here we want to get the language down right. If we said the third power, that would be like x to the third power, right?
Right.
But that's not what we're talking about. We're talking about this base 3
Mhm.
to the power x. Okay.
Okay.
So what you guys should see, this pattern should be very like easy to pick up here, is that if we have log base 3 of x, that is the inverse function of 3 to the x power because they share the same base. Okay. So if I gave you log base 4 of x, which exponential function does it come from?
4x.
4x.
Not 4x. We have to be very clear
4x.
here
Oh,
because 4x is 4x, right?
So we have to
Well,
say
4 to the x power.
You have to say 4 to the
4
x power
x
because
power.
these guys are not the same. Okay. And the only reason I'm being a real stickler here is because, maybe I should have been more of a stickler when we started talking about roots and we said, oh, square root and square root and square, because like they sound the same, but it's easy to
Mhm.
confuse yourself. They're not the same. But if you're going to understand these logarithms, you have to say it correctly. So it's 4 to the x power, not 4x. Okay? All right. And that's exactly right. 4 to the x power is the exponential function this comes from. Okay? Log base 5 of x is the inverse of what?
5 to the x power.
5 to the x power. Okay? And then you could see even weirder things like log base pi of x. And it's not a trick question here. What's the exponential function that we expect?
Pi to the x power.
Pi to the x power.
X power.
Are you guys okay with that?
Yes.
Okay. And like I said, we're not going to go through the whole shebang of like graphing all of these different functions, but you just need to understand that for every exponential function, it has a corresponding inverse that we're going to call log base whatever, log base b, whatever the base is. Okay. Okay. So these logarithms contain the same information as an exponential equation, essentially. In the same way that, multiplication and division, you have learned since grade school that those are opposites of each other. Like if I said, oh, 6 times 7 is equal to 42. You guys are comfortable with that equation in terms of multiplication, right? 6 times 7 is 42. Is that correct?
Yes.
Okay.
Yes.
If I then told you, well, like if 6 times 7 is equal to 42, that also means that 42 divided by 7 is 6. Are you okay with that?
Yes.
Right?
Yeah.
Both of those statements, whether I put it in terms of multiplication or division, mean the same thing. They contain the same information. Okay. So here we understand something about exponentials because like we've been dealing with exponents in this class and before this class. If we had something like 5 to the second power equals 25, we can call that an exponential equation, and we should be able to convert that to a logarithm. Okay. How is that going to go down? Well, that's going to take a couple of steps. So let's say that we're starting off with this exponential expression or exponential equation. Okay. I'm going to label the parts of this equation so that we can give a name or a label to everything. Remember, this big number that we have at the bottom is called the base. This number that we write as a superscript, the little number in the corner, we call the exponent. And then this number over here, on the other side of the equal sign, you can think of that like it's the output, but sometimes it's called the argument. Okay, so I'm just going to give you those vocabulary terms just in case you hear it sort of described that way when you're talking to one of the tutors in Math World, or if you hit that view example button in Alex, it might describe that as the argument. Okay, so what we want to be able to do is take this expression 5 to the second power equals 25, which should be no surprise to anybody that that's a true statement. And we want to take that statement and write it as a logarithmic equation, or just a log equation, if you want to abbreviate it. Okay. The way we're going to do this is we're always going to start by writing the word log, and then we're going to write the base of this exponential. So this base was a 5, so I'm going to put a base 5 here as a little subscript, base 5. Okay. Then I'm going to open up some parentheses and put an equal sign here. And what we want to do is figure out what's going inside the parentheses, what's going on the other side of the equal sign. Okay. Well, if you think about this exponential equation, it's kind of like an exponential function where we had 5 to the x power equals some y value, right? Where I said, like, let x equal 2. And then we took that 2, plugged it into the function for our x value, and then we got our y value as the output. Okay? If this is the exponential function that we're talking about in this equation, and we're going into a logarithm, which is the inverse, then the position of the x and the y value in this equation should swap. So we're going to swap the position of the x and the y. So over here in the world of logarithms, we're going to write this as if this was our x value, this exponent of 2, and this is our y value, the 25, I'm going to put the 25 inside of the log function,
There you go.
and then it's going to equal 2 over here.
2.
Okay. So the original output or argument goes inside the parentheses, and then the log function is basically spitting out the exponent. Okay. So I've used this analogy in the past, and I really love it. Also because the 1980s classic Karate Kid is just a great movie. If you haven't seen it, you should definitely watch it 2 or 3 times. I would I could take or leave the Cobra Kai series, but the
How did you like
original,
the movie?
I have not seen the movie. My brother said it was worth passing up on. Just watch it when it streams.
I don't know, because it integrates both of them. I don't want to ruin it, so I think
Yeah,
it's
yeah. Okay, so we got one thumbs up. My brother is definitely giving a thumbs down, but
Thumbs down.
take that for what it's worth. Okay. But like Daniel in the Karate Kid, we're gonna practice some of these just so we can get that muscle memory down. Okay. So let me give you another exponential equation and we're gonna convert it to a log equation. So let's do something really simple like uh maybe 3 to the fourth power equals 81. Okay. This is true. You can check it in your calculator if you wanted to. Like it might mean not something that you're super familiar with, but 3 to the fourth power is equal to 81. Okay. So if it's given to us in exponential form, you're just going to follow these steps. First, write the word log, and then tell me what is the base of this exponential equation.
3,
So I'm going to
3.
put log base 3,
3.
open up the parentheses, put the equal sign down. Then, because a logarithm is an inverse of an exponential, I'm going to take the x and the y, and I'm going to swap their position. So I'm going to put 81 here
1.
and 4 over here. And that's it. Any questions there? Okay. And so remember how I said like a logarithm is like we're in Mexico and we want to convert to back to dollars? If this is taking an exponent and then spitting out some number, the logarithm is really asking you 3 to what power equals 81? So basically, it's asking you, what exponent do I need to raise this base to get this number on the inside?
The fourth power.
And we have to raise it to the fourth power, right? So really, these are two ways to talk about the same kind of information. 3 to the
Mm-hmm.
fourth power equals 81 is the same as saying log base 3 of 81 involves the fourth power,
Hmm.
right? Okay, so let's do another one so that we can just have some more practice here. Let's say I gave you guys 2 to the fifth power is equal to 32. I think that's right. I'm just going to double check that. 2 to the fifth power is equal to 32. Okay, good. So go ahead and write this in logarithmic form for me. What do I need to write down?
Log
Log
base
Base 2.
2,
base 2. Open up some
parentheses,
parentheses.
32,
2.
32 goes inside,
and 5 goes on the equals.
and 5 goes on the other side of the equal sign. That's perfect. You guys okay with that? Does that feel okay?
Yes.
Yeah,
Not too crazy.
like musical chairs.
Yeah, it's kind of
See,
like musical chairs. Okay. And like maybe in grade school, I don't know, when I came back to teach myself math over again, which is a whole long story and we won't get into it, I remember learning how to teach multiplication and division, but mathematicians came and said, "Oh, well, 27 divided by 3 is equal to 9 because because 9 times 3 is equal to 27." And I was like, I don't understand what's going on here, because these seem like really trivial facts. But it turns out that when you're talking to a mathematician, multiplication and division are the same thing because they store the same information. I could say in this division problem over here, if I just kind of reverse the operation, 9 times 3, it gives me 27. And so like a lot of the processes that we've been doing in this class when it came to like factoring a number and looking at all the factor pairs was really breaking up these larger numbers and like kind of reversing the process of multiplication. In fact, that's what factoring is. It's kind of reversing a distributive property, which is the reverse of multiplication, just in more complicated scenarios. Okay. So we kind of have been doing stuff like this before where we want to convert something to some other form because maybe it's going to be easier to work with stuff in this logarithmic form as opposed to exponential form. Okay. But there are also scenarios where we'll get a logarithmic expression and need to convert that back to exponential form because sometimes the exponential form is easier to work with. Okay. So just like the 1980s classic Karate Kid, once we wax on, we need to wax off. So
Wax
that's
off.
exactly what we're going to do here. Okay.
And see, I come across logarithms, and it wasn't explained this way.
Oh, really? Where do you come
It,
across logarithms?
at SAC with
Okay.
another
What
teacher.
class?
It's the same class. I'm a
Mhm.
repeat.
Okay. No shame there. A lot of people are. But yeah, I mean, sometimes you just need to like, we don't choose the families we're born into in the same way we don't choose the classes or the professors that we end up getting. But like once you find the right one, it's the right fit and it just feels completely different, right? Uh,
Because it just you teach it different. I understand it clearer because I'm like,
yeah.
okay, why he didn't explain it like this?
Yeah, I'm telling you, I think that part of it is just being a younger teacher, but also like I'm a Hispanic male from San Antonio. Like, I love the culture here. I've mentioned to you guys before that I have a blended family. My parents are Mexican Americans from El Paso. My stepdad is a black man from San Antonio. He's got family out in Alabama, out in Seguin. So like I've talked with a lot of people from a lot of different cultures. I mean, as I've grown up and gone to different schools, I've gone to school in Kerrville where there's predominantly white folks out there,
Mm.
right? And then I've gone to UTSA and taken some classes where there's predominantly Chinese students or even Middle Eastern students. And so learning how to navigate different cultures is a really good skill. And like when I bring what I bring to the table as a teacher now is that, you know, I struggled with trying to understand this material and making it make sense for me, but then taking it back to the people and saying like, here is what it means in plain English, and it could be like, oh, this is how we say it in plain English, senora, if I'm talking to a Mexican American or a Latin American. Or it could be like, yo, this is how you do it, dog. Like it ain't that hard, right? And you just code switch and you just speak to the people as needed. But it shouldn't be that hard. And there's all kinds of walks of life that come through St. Philip's, and that's kind of why I like being here, because I feel like I'm able to make this stuff connect in a way that your math textbooks definitely won't put it this way. So one day, my hope is to create a YouTube channel that I'm gonna call X Gon Give It To You, and every time I solve an equation, I just play DMX and solve equations the whole way.
Yeah.
But putting all my dreams aside, converting these logarithms is a very easy. It's a two-step process, right? Identify the base, write your parentheses, equals, and then swap the position of the x and the y, and that's going to be good enough for government work, okay? So we're going to have to do that backwards and forwards. So we've already gone through some practice doing this forwards. So 5 to the second power equals 25 is the same thing as log base 5 of 25 equals 2. 2 to the third power equals 8. Can you guys give me that as a logarithm?
Log base 2,
Mm-hmm.
parentheses 8, equal 3.
That's exactly right. 3 to the fourth power equals 81 is something that we did already, so that's going to be log base 3 of 81 equals 4. But even something that looks more intimidating with these big numbers, again, don't be afraid if you get a fraction or if you get big numbers. 10 to the fifth power equals 100,000. Can you guys tell me how I would write that as a logarithm?
Log base
Log base
10,
10,
Log base 10
parentheses,
100,000 in
100,000
parentheses
Mm-hmm.
equal 5.
equals 5.
That's exactly right. You guys like racing right there, neck
Battle.
and neck, right? That's
I
exactly
was trying to keep up with Corey's tone.
right. I'm gonna need a 3-part harmony on the next one, guys. So okay. So one thing I'm gonna note here is that whenever we're dealing with base 10 is something that's used a lot in science and mathematics, and it's used so much that they call this, when we switch it over to a logarithm, you'll notice that we don't put a base 10.
Yes.
So if you don't see a base 10, then it's an understood base 10, and we call that the common log. And I'm going to have a slide here in a little bit that reiterates this point, but the common log is log base 10, and we don't show the base here. Okay. All right. One last one here. Can you guys convert 2 to the negative third power equals 1/8 to a logarithm?
Log 2,
Log base 2,
parentheses 1/8
parentheses 1/8.
equal -3.
That's exactly right. Okay, so the process is the same, regardless of me throwing a fraction at you, maybe throwing a negative exponent at you. It's going to be the same. And then on this slide, I also say log base 10 is sometimes called the common log, and we typically don't write the base 10, okay? So just remember that. Then, like I said, maybe a little while ago, we're going to have to convert in the reverse direction. So if I gave you log base 7 of 49 equals 2, how would you convert that back to exponential form?
It's gonna be
7 squared equals 49.
Yeah,
yes.
that's exactly right. So
Yes.
I always think about writing the base first. And remember, when you're not in log form, you don't have to write the word log. So it's just 7 to the second power equals 49. And that kind of makes sense with what I explained earlier, that this logarithm is really saying 7 to what power gives you 49? Well, that's the 2. Okay. Okay, so let's get some more practice here. Log base 3 of 27 is equal to 3. Write that as an exponential form. What's the base?
I didn't have my audio on. 3.
Oh, there you go. Yeah. Helps to unmute yourself. So yeah,
Yeah.
3 is the base. What's the exponent?
3.
3. And that equals?
27.
There you go. 3 to the third power equals 27. So you write the base, you plop that exponent back on, and then the stuff in parentheses is what it equals. Log base 4 of 1024 is equal to 5. How would I write this as an exponential form?
4 to the power of 1024.
No.
Oh, sorry. 4 to the power
4 to the
of
5th
5.
power
Yeah, to the 5th power.
equals 1000.
Sorry, I just started reading it.
Yeah, yeah. So sometimes we need to stop our brains from doing autopilot things. Remember, you got to swap these guys. So if it helps, you can just say, take the 4, take the 5 equals the big number over here. Any questions about these? Is this feeling okay?
Yeah.
Okay, well, my PowerPoint's a little bit incorrect here for this next one, because I meant to go from log form to exponential form. But let's say I give you this exponential form. Can you convert this over to log form for me?
Log 10.
Log base 10.
Oh, sorry. Base 10.
Yeah.
Wait.
It's log parenthesis 1,000,000 equals 6.
That's right. So if we are not showing the base 10, you don't have to show the base 10. If you were to write that down on paper, I would accept it. But I think that Alex won't. So if you just write log of 1 million equals 6, then that's the way it's going to go, okay? Okay. And just remember, as you work through these problems, the common log, you don't have to write the base. You just have to remember it has a base 10, and that's just understood. I really hate that mathematicians do this, but they're always saying like, oh, there's an understood coefficient of 1, there's an understood exponent of 1, there's an understood index of 2 on the square root. Well, now for logarithms, there's an understood base of 10 if we don't see a base, okay? All right, so this is going to be an important note, and we've already talked about the common log where we don't have to show the base 10, and it's understood that that's what the base is. But there's this other fancy logarithm called the natural log, and it's written as ln. So if you have your calculator next to you, on your calculator on the left side, you see a button that just says log,
No.
and that's going to be your common log. And then right underneath that, you should see a button that says LN. If you have a TI-84 that's like mine, that's in capital letters, okay?
Yes.
But if you have a TI-84, I think the plus CE or CE plus, I always forget the order, it looks like lowercase ln, and students often confuse this with a capital I, okay?
A button at?
That what's up?
Where's that button at? I see the log.
Is it right underneath the log where
It
you
should
have
right underneath.
LN?
Oh, okay, yes, I see it.
Yeah.
Oh, okay.
So that log and that LN button are very particular. These are the most used logarithms in science and mathematics. So for instance, if I needed to count like a million or a billion stars, like I'm taking a survey of the night sky and I'm an astronomer and I needed to count a billion, a trillion things, it's nice to put the number a billion or a trillion in here in that common log because as we saw with that last example, let me see if I can back up. Over here, when we have the common log of 1 million, if I put a big number in a logarithm, the logarithm spits out a really small number, and smaller numbers are just easier to work with, right? So a lot of times when we have to count things like stars in the sky, or even the number of molecules in like a beaker, then
Mhm.
that can be a really large number. Plugging that number into a logarithm will spit out a smaller, more manageable number to work with. So that's why the common log is often used in science and mathematics. Okay. The natural log is something that comes up in a lot of engineering problems because as we introduced yesterday when we were talking about the exponential function base e, I think that we mentioned this. This is Euler's number. 2.718 is its approximate value, but e is so common in calculus, engineering, and other scientific applications that we gave it its own logarithm. So instead of putting log base e, we're just going to call that the natural log. So whenever you see the natural log of like 5, just know that that's the same thing as log base e of 5. If you need to write that base explicitly, then do it just to remind yourself what the base is. But otherwise, we're not going to show it. We're just going to understand the natural log has this base e. Okay, any questions or comments there? Okay. I forgot that I actually merged this PowerPoint with the next PowerPoint. So we're going to hold off on the properties of logarithms until tomorrow because what I want to do is just give you guys practice finding things on your calculator with these logarithms. So what I'm going to do now is we're going to go back over to Canvas and we're going to sort of work one of these worksheets together. I love being able to do these worksheets with you just because I can sort of coach you through understanding these worksheets. And the second consequence of doing that is that it's a free 100 for you guys, or gets you really close to getting a free homework assignment there. So
Maybe
what we're going to do is go into module 4 and pull up this worksheet, understanding logarithmic functions. And then we're going to work through some of these if you guys are okay with that. Okay. For these, I'm going to write them down on paper, and then we're going to work them out. Actually, whenever we need let's see, do we need to work them out on paper? I feel like we can work these out on the screen, but um, I do want to work them out on paper actually, just so I can show you where the different log functions are on the calculator, okay? Because that's kind of hidden in different parts of the calculator. So the common log and the natural log are on center stage because you should be able to see those buttons on the left side of your calculator. But whenever you want to change the base, then that's going to require a little bit of steps to figure out where that is. So uh, can you guys see this worksheet here?
Yes.
All
Yes.
right. This first page has questions A through F. We're going to go through them together. And it says, without a calculator, use the conversion formula above to convert the exponential equation into a logarithmic form. Okay. So we're going to start off with 2 to the third power equals 8. And this stuff doesn't really require the calculator, so maybe we could just do this on the screen. But can you guys convert this to log form? What would I write down?
Log 2.
Log base 2.
Oh, yes. Writing that down.
Yeah.
Of 8.
Of
8
8
equals 3.
equals 3. Any questions, comments there? I feel like we kind of beat a dead horse with these already, and I think you guys should be pretty good at this now. So, um, does anybody want to venture a guess on how to write B in logarithmic form?
I'm gonna have my comeback.
Yeah, let's see it. Redemption.
Log base 7.
Log base 7.
Oh gosh, parentheses,
Parentheses.
49
49
equals 2.
equals 2.
And the crowd goes mild.
Yeah.
Okay.
Crowd goes mild is fantastic. All right. Okay, does anybody want to, throw down for part C here?
That's log of
10,000.
10,000 equals
Log.
4.
Of 10,000.
Gina, do the next one.
Equals 4. Huh?
Eating up.
Do D.
Well, yes, you gotta call me out.
Okay,
Uh,
Gina, do you think you got this one?
yeah, I just got volunteered for tribute. No, just kidding.
Yeah. Here's the sacrifice.
Log of the base 4.
Of the
Per-
base 4 is not correct.
Just
Log
base.
base 4.
No, it's not even 4. What's the base?
Oh, half.
1/2, yeah.
1/2.
What goes inside the parentheses?
1/16
1 over
There you
16
go. There you go.
equals
It's cooking.
equals 4. Are you okay with that?
Yay, Gina.
Yeah, so remember, you really don't want to trip over yourself here. The number down here, the big one, even if it's a fraction, that's going to be the base. Okay? And then you put this guy in the parentheses. Maybe that'll be helpful. Then you put this guy in the parentheses, and then this guy, the exponent gets spit out on the other side.
I find it helpful when I'm not messing up my vocabulary to write out B equals, blank, X
Oh,
equals
yeah.
Y equals blank to kind of keep it organized in my head.
Yeah, and honestly, that's what I should be doing, labeling these. I had a student earlier this morning that was like, I'm sorry, sir, I'm going to have to label these every single time. And I was like, I don't know why you're apologizing. do it, right? As long as you're getting it correct. I don't understand where this shame is coming from, but just like do what you need to do so that you remember. Okay, so let's do the next one. What are we going to write down for E?
Don't worry, guys. I got this.
All right.
Log base 1/3.
1/3 or 1/3
Mm-hmm.
There, yeah. Parentheses 243 equals -5.
equals -5. That's correct.
Mic drop.
Yeah. Then does anybody want to volunteer for this last one?
Corey, that's all you.
Oh man. The only thing I can look at is log base 8 and
Log base 8.
parentheses 1 equals 0.
That's correct. Not too bad, right?
Yeah.
Not so bad.
See, you explained it differently. It was hard last time.
We're gonna have
Yeah,
to go
I
to
mean,
that teacher.
I'll tell you this. There is one tutor that during the spring and the fall semester, she's one of my favorite tutors. But like I said, she also works at Central Catholic, or actually, she retired from teaching math at Central Catholic, and she's this 70 mid 70s year old woman who's very adamant about teaching it the right way. And so
Wait.
if she could, she would get out her ruler and smack people's wrists if they got things incorrect or if they didn't understand something. Some people respond positively to that kind of pressure. I'm the kind of student where I can take some punishment because I was raised Catholic, but
Yeah.
not everybody responds positively to that. So I'm trying to meet you where you are. And like I said, if you had another instructor that made this way more complicated than it needed to be, well, then that is just a crappy hand that you were dealt, right? But we're here now. We're here now and we're getting
We
it,
here
and
now.
that's what matters.
We here now.
Yeah. All right. So I want to show you guys for maybe one of these harder ones that you can check your work in the calculator. Like let's look at D, which was 1/2 to the 4th power equals 1/16. And we said that that converted to log base 1/2 of 1/16 equals 4. Okay. So for a moment, just bear with me. Let's go back over to the document cam just so that we can pull up the calculator. So let's say that this is what you got when you made that conversion, and this is correct, but when you're working on your homework late at night and nobody's there to hear your screams, sometimes we start to second guess ourselves, okay? So it would be really nice if we had a way to check ourselves before we wrecked ourselves, right? So what you're going to do is turn on your calculator, and we're going to type log base 1/2 of 1/16 equals 4 into the calculator. So if you have a TI-84 or a better model, what you're going to do is click on the math button, okay? Math button should be on the left side, right under the alpha button, math. Then we're going to scroll all the way down until we find something that says log base. So there's this log base function, which is all the way towards the end. It's the second to the last thing. It's option A. I'm going to hit enter. And so now I have this expression on my calculator, log of base blank, with parentheses that are also blank. So now we can type in whatever we want for the base and whatever we want for the input. If we need a fraction here, this is where we're going to double up, and we're going to put alpha y equals enter, and now we can put a base of 1/2. Then we can go back into the input inside the parentheses and then put alpha y equals yet again to put 1/16, because now we're just checking to see, does that really give me 4? And if I hit enter, it does. Okay. So just remember that we're going to press the math button and then go find the log base function so that we can get log of blank, sorry, base blank of blank, and then we can fill in the blanks. Does that make sense? Was that clear? I feel like my brain went to
Yes,
mush
but
towards the end there.
when you hit math, you can also do alpha A and it'll automatically select it.
Yeah. I usually don't like doing that. What I'll do is go math and then I'll just go up twice.
Oh, cool.
Yeah. It's the same number of keystrokes, but finding alpha and then A. Oh, I guess it's basically right there as well. So yeah, you could do alpha and then math again to get it. Okay. But yeah, I like to think of those calculator functions, in that list as being kind of like Pac-Man, where you go out one side and then you come out the other side. So instead of going down, I just go back and then I come out the other side, like I popped out of a black hole of the other universe or something. Okay. So another one that we just did was, let's see, we did E, which was 1/3 to the negative fifth power equals 243. And we got log base 1/3 of 243 equals -5. And then again, remember, you're going to be up late at night working on this stuff. You're going to start to feel insecure and you're going to want to check yourself. So we're just going to go math, log base, put our fancy fraction in. 1/3 is our base. 243 is the input, and we get -5, and all is well in the world. Okay. Any questions, comments about that? That seem clear enough? Well, if not, you can review the video. I think that you guys probably are sharp enough to understand that. So let's look at the next page of problems here, right? So again, my favorite analogy. The older I get, the more I realize that students haven't seen Karate Kid. But in an evening class, usually I have an older crowd, so we have seen that classic. So now we're going to wax off. We're going to convert these back over to exponential form. Okay.
Hmm.
So if I have log base 4 of 16 equals 2, how am I going to write this in exponential form without a calculator?
4 squared
4
equals
squared
16.
equals 16.
4 squared equals 16 is perfect. Okay. And then that one you can sort of do a gut check because you do know that 4 to the second power is 16. That should make sense. With slightly bigger numbers, it's going to be harder to do that, but you can also just check those exponentials in the calculator. So the next one's going to be what?
5 to the third power equal 125.
That's exactly right. Any questions, comments there? Somebody want to give it a go for problem C? And here I did show the base 10, kind of, approaching you guys with the kitty gloves here a little bit, but I don't have to put that base 10.
It's 10 to the 6th power equals 1 million.
10 to the 6th power equals 1 million. And that was actually one that we saw in the PowerPoint. So I'm not trying to take anything away from you guys, but that one was in the PowerPoint, just making that observation. Okay, the next one is going to be written as what?
1/10 to the power of 2.
Wait, you skipped.
I skipped. Oh, okay. I'll do both.
Yeah.
Well, let me just equals 100
So you said 1/10 to
power
the
negative
power -2 equals 100. That's correct.
Sorry about that. And
No,
then
you're fine. Actually, let me make a note here. Whenever we have a base that's a fraction,
Mhm.
I would always put parentheses over that entire fraction before I stick the exponent on it. And the only reason is because if I were to see 1/10 raised to the -2 power without parentheses, in my brain, I'm thinking that only the 1 gets the exponent.
okay.
So a clearer way to indicate that the entire fraction gets the exponent is to use those parentheses. Okay,
Thank you.
not a problem. Okay, so we're gonna back up and do that other one.
Yes.
Let's go.
2 to the power of -5 equals 1/32.
Yeah, that's good. And actually, let me make another note here, right? This
Oh,
makes
sorry.
sense. This makes sense if we think about our negative exponent rule, because if I have -5 as my exponent, I'm going to flip the base to 1/2, right, instead of 2. And then if I were to apply the fifth power, then 1 to the fifth power is 1, and 2 to the fifth power is 32. So, we could check that in the calculator for sure. I'm not trying to like flex on anybody here, but I want to continue reiterating that negative exponent rule, that it exists, and we're probably going to see it next week. So don't just like cast that into the shadowy realm of, the recesses of your brain. It's going to be useful a little bit later on. So just wanted to remind ourselves that that's a thing.
Can you write that again really quickly?
The negative exponent rule?
Yes.
Yeah, let me go ahead and put that stuff back, actually. What am I doing? Going the wrong way. Did you want the whole rule again? The b to the negative x power becomes 1 over b to the positive x power. Okay. But does anybody want to go ahead and
Thank you.
convert this last one to exponential form for us? What would this one look like?
Pi to the power of 0 equals 1.
There we go. Pi to the power of 0 equals 1. And anything except for 0 raised to the 0 power is equal to 1. In one of the videos I'm going to post to Canvas a little bit later on, I briefly mentioned 0 to the 0 power. This is not something that we're ever going to experience in our class, but this is something that comes up in like deep physics, and that is undefined. So we're never going to raise 0 to the 0 power because nasty things happen when you try to do that. So we're just going to leave it off the table for our class, okay? But anything else raised to the 0 power is always going to give you 1. And you could verify that in the calculator, okay? Questions, comments about these examples with a few of those little side notes thrown in. Okay. Anybody need some more time to write some of this stuff down? Or are we good to go?
Okay.
I'm thinking we're good too. Okay. All right. Well, now for this third problem set, we have a laundry list of things to evaluate in the calculator, right? So this is evaluating a function, and the function that was given is log base 3 of x. Remember that this is related to that worksheet that we did yesterday where we started with the function 3 to the x power. This log function is its inverse, okay? So you're going to use your calculator and you're just going to, for these, type in log base 3, because that's the function we're working with. And then if you see evaluate f of 1/9, we're just going to put 1/9 inside the logarithm and then figure out what our y value is. So here, I don't want you to worry about, are we swapping the x and the y values? There's not going to be any of this swapping. Whenever we give you a function to evaluate, we're going to treat this as the input value, the 1/9, and then whatever we get as our output is going to be our y value so that we can graph this. So what we're looking for is 1/9 comma something so that we can plot that point. Okay. So can you guys throw that into the calculator and tell me what you're going to get for your y value here?
-2.
Yeah, that's right, -2. Anybody have any questions there? Does anybody need me to show how to get that in the calculator? Or are you guys good? Even if one person needs me to show that on the calculator, I will do it. Okay. In fact, let me just do it anyway,
Hmm.
just to make sure we have it for the recording, right? So what we're trying to evaluate is f of 1/9, where the function is log base 3, and we're just taking that 1/9 and putting it into the function, right? So in our calculator, we'll just go to math up twice to get log base, put log base 3, then we're going to put our fancy fraction, alpha y equals, and then we're going to put 1/9 there, and then we get -2. Okay, so because we're able to use the calculator here, it's not going to be like this long, arduous process. So you need to accept when it's just that simple, okay? Where things could go wrong is like maybe thinking it needs to be more complicated than it is, or if you're getting these wrong, it could be that you're just typing stuff into the calculator wrong, in which case definitely go to Math World and talk to somebody so that they can set you straight on what it is you're typing in the calculator, okay? But they should be very straightforward. The next problem on the worksheet says to evaluate f of 1/3. Okay, so literally we're just going to take this function, log base 3, and plug as our input 1/3, and that's equal to what?
-1.
-1. Okay, so the ordered pair I should have here is 1/3, comma, -1. Are you guys okay with that? The one we found above was 1/9, comma, -2. Okay, so go ahead and find the rest of them. I'm going to give you guys maybe a minute to do this, just so you can get some practice here in your calculator. I'm just going to be awkwardly standing by for the next minute, minute and a half to see if you guys can find these. And just go ahead and put ready in the chat when you are done. Okay. Got a few people ready already. I'm just going to slowly put my answers down.
Hmm.
More people are ready. Okay. Anybody still working on this? Anybody running into some trouble?
Yeah, that's negative.
Yeah, those last two should be some trouble.
I'm zeroed out.
So when you put log base 3 of 0 in the calculator, well, let me kind of back up a little bit. I'm going to draw something here over in the side so we can talk about these log functions. I don't want an orange arrow. I want a black arrow. There we go. There's my x-axis. There's my y-axis. And these log functions look something like this. The sound effect is required. This point right here is the x-intercept at 1, comma 0. There is also a, let's see, what color do I need? Red, maybe? Vertical asymptote that's aligned with the y-axis. Okay. Okay. So if I'm thinking about these logarithmic functions, and this is just a generic log function, can you guys remind me what the domain of this function is? How far to the left does this graph go?
+1?
So it does go to +1, but doesn't the graph pass the +1?
There's 0.
Yeah, it goes all the way to 0, but doesn't cross 0, right? So 0 is not included in the domain because we have a vertical asymptote that's like a stopping point. So on the left, this graph goes all the way towards the y-axis, but doesn't cross it. So 0 is where the domain begins, and then the graph veers off to the right forever towards positive infinity.
Infinity.
Okay, and this is the domain. We put a parentheses on that 0 because we have a vertical asymptote. And if you remember vertical asymptotes from our discussion of rational functions, those are restricted values, right? So what that means is that when you plug 0 into a logarithmic function, what you're doing is trying to plot a point on that vertical asymptote, and you simply cannot do that, right? It's not going to produce a y value. So instead, what we're going to write whenever we have to plug 0 into that function, any log function, we're going to say that this is undefined, okay? Because the x value of 0 is not in the domain of this function, so I can't plug it into a log function.
And it wouldn't be 0, comma 0.
So it's not going to be 0, comma 0. I'm
Okay.
not even getting a y value.
Y
I
value
can't get a
here.
y value.
Okay.
Because like if it were 0, 0, then that
Oh,
would be
yeah.
like saying I have a
Yeah.
point
Point right in the
right
middle.
here, but I can't have a point on a vertical asymptote. Okay.
Okay. That's what
So
I
we
thought.
just simply
Undefined.
do not have a point here. There is no y value possible. Okay. And then also, if we kind of look at this graph, the domain is very clear. This function only takes x values that are greater than 0, which means that all of these negative numbers like -1, -2, -3, and so on, none of these numbers can be put into log functions either. So if you're trying to put log base 3 of -3 in your calculator, you're getting an error. And that error is a little bit different from the domain error when you plug a 0 in. Your calculator might be saying non-real answer. But the reason why it's saying that is that because there's a complicated branch of mathematics called complex analysis that is well beyond our pay grade. It's not something that we're going to cover in this class, but there is this like fancy workaround where even though we're not supposed to put negative numbers into logs, nerdy mathematicians figured out a way to make that work, but it involves imaginary numbers. And again, we're not going to worry about that. So what we're going to do whenever we plug a negative into a logarithm, or whenever we're forced to plug a negative in, we're just going to say that's undefined also.
Fine. Okay,
Okay.
thank you.
Yeah, so you can only plug numbers that are greater than 0 into logarithms, so positive numbers. You can never plug 0 or any negatives into the logarithm. And there's a little asterisk on that. There is one caveat. And what I mean by that is, imagine for a second that we took this graph and we said this is a parent function. And this is the graph, let's just say it's log base 3 of x, right? What if we took this function log base 3 of x and we said, let's change it to log base 3 of x plus 4? What happens usually when I add 4 inside the parentheses of a function? Think about your transformation rules for graphs. If I add 4 inside the parentheses, how will my graph move?
It moves left.
Shifting up,
No, so if I'm inside the parentheses, it's going to shift left.
shift left.
Yeah. So if this one shifts left by 4 units, I can't spell units today. If we shifted this entire graph over by 4 units, then the vertical asymptote moves to x equals -4, right?
Mhm.
And that would mean that my graph would move to looking something like this. In which case the domain has changed, right? And now I can plug some of these negative numbers in. For instance, if I took x is equal to -1 and plugged it into this modified function for x, plug it in for the x, then that would be log base 3 of -1 plus 4. And what is -1 plus 4?
3.
Yeah, and that's 3, which is a positive number. So that would be okay, right? But in general, when we're just talking about the parent function and we're not talking about having shifted the graph to the left or to the right, then we won't have to worry about that. The domain will be restricted to just the positive numbers. So everything over 0, but no negatives. Okay. So that's something that we may have to watch out for in certain circumstances, but for the most part, I think that that's okay. What this means is that for these last two problems here, we don't have to plot them. But we now have a collection of ordered pairs here so that we can graph our function. So let me just write these down in a table. My x values are 1/9, 1/3, 1, 3, 9. And then the y values that I got were -2, -1, 0, 1, and 2. And with that, we can go ahead and graph this, okay? So I'm going to clear some of these just so we can move to the graphing portion here. Scrub-a-dub-dub. Okay, I'm going to leave those ordered pairs up and I'll add the rest of them later, but let's scroll down here to our graph, right? So the other ordered pairs that we have are 1 and 0, 3 and 1, and then 9 and 2. Are you guys okay with that?
Yes.
Okay. So now we can set up our graph. Remember that because this function, log base 3, has not been shifted left, right, up, or down, then what we should understand is that we're going to have a vertical asymptote overlapping the y-axis. Okay, so I'm just going to count by ones. I think that this will be good enough. And I think that graphing these in the reverse order is going to make a little bit more sense just because we have some whole numbers that we can work with. So 9 comma 2 is going to be over 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 2. So that's right here. You guys okay with that? 9 comma 2? 9 comma 2. That takes care of this guy. Then 3 comma 1 is going to be over 1, 2, 3. This is 3. Comma 1 is going to be right here. That takes care of this guy. 1 comma 0 is going to be our x-intercept there. And then here's where it gets a little bit dicey. 1/3 is like here-ish, real close to that asymptote, right? So we're just going to go drop down to a -1 down here. And then 1/9, if you compute this as a decimal, it's going to be 0.111 repeating, which is even closer to that asymptote. So that's going to be down here-ish. So you kind of see this, I don't know if you can think of it like a trumpet, but like it's a curve like so, and that's going to be good enough here. Okay. Anybody have any questions with graphing this? Questions or comments? Just remember that if you're not sure where that fraction belongs or where it goes in terms of your x or your y axis, just always convert that to a decimal and it'll be easier to think about that way. Okay. But then again, in Alex, you will be able to type in fractions. So, always keep those fractions on deck in case you need to just type those points into Alex. Let Alex do the heavy lifting there. Okay. So here for question I, it says, describe how this graph of the logarithmic function, log base 3 of x, compares to that graph of the exponential function 3 to the x power from the last worksheet. And so all I'm looking for here is for you to connect the dots that literally, not literally, figuratively, remember that this exponential function that we looked at on the last worksheet, when we graphed it, looked something like this, right? Where it was that reflection across the identity function. So all I'm looking for in terms of your answer here, your response, is just to say that the log function is the inverse of the exponential function. So it appears reflected across the identity function or the diagonal line. And then I'm just going to make this text box a little bit bigger, maybe make the text a little bit smaller. I'm not sure if I can. There you go. The log function is the inverse of the exponential function, so it appears reflected across the identity or that diagonal line. Any questions or comments about that?
No.
Awesome. Okay. All right. Do you guys mind if I erase this stuff now?
Go ahead.
All right.
Race away.
Okay.
Okay.
So this last problem set, I'm going to let you guys do on your own, and I'm going to end the lecture here a little bit early just because I'm sure you guys have had enough. But I do want to kind of guide you here as you get started and finish up this last set, because it's going to be a lot of the same thing that we did with that third problem set. We're going to evaluate this function, but now this is going to be the natural log function. So when you evaluate these in the calculator, we'll write out the natural log of 1 over e squared. And it's a little bit complicated looking, but like your calculator is going to spit out a nice number here. Actually, your calculator should spit out, I think, -2 here. Okay. If somebody wants to check me on that, please do so.
Where's the
That's
E
correct.
square?
That's correct. That's correct.
That's correct. Okay.
How do you push in the E square?
Okay, so let me do that, right? This is one thing I wanted to guide y'all on, so that everybody's on the same page. When you type this one into the calculator, you're gonna hit the ln button. Are you okay with that?
Mhm. Yes.
And then the e squared, there's two ways that you can get it. The easiest way is probably to hit the second and then the ln button again, because now we can put e to some exponent. And then we can just put the exponent of 2 in and then close up the logarithm. Okay, so sorry, I typed that in incorrectly though. That's just ln of e squared. What we really wanted was the natural log of a fraction 1 over, and then we'll hit second natural log. And so it's 1 over e squared, and then we'll go ahead and close up the parentheses, and that's where we're getting -2. Was that a little bit clearer? So if you just look at your calculator, second natural log is one way that you can get that e. But if you don't want an exponent, you can also do the second and then the division button, and you'll also get that e, which is Euler's number 2.718, blah, blah, blah. Dun, dun, dun. Okay. So hopefully that was clear. So I want you guys to just evaluate these functions, right, with the given input value, and then find the y value. And then you're going to do the same thing that we did with the previous problem. So you're just going to graph it, make sure that you have your asymptote at x equals 0 aligned with the y-axis. But it should be pretty manageable, okay? So I want to just leave it there so that you guys can do that on your own. This worksheet's going to be due tomorrow, so just make sure you get it knocked out. If you need some help, you can always pop in with MathWorld and have those tutors check the work that you're doing, okay? So if you want, you can hang out with me for a few moments after I dismiss, and if you have any questions, I can answer those things. But otherwise, I think we're going to leave it there, and I'll see you guys tomorrow.